Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to learn about memory management in operating systems, with our focus being on associative memory. This is part 7 of a 9-part series of videos or presentations on this topic on memory management. My name is Memeji M, or you can simply call me Emily Swap. Under associative memory, we shall look at the introduction, or what we call the basic concept in associative memory, the purpose of associative memory, and the parts of associative memory. Associative memory is also called the TLB, or translation look aside buffer. This is a small, special, high-speed memory, fast lookup hardware cache that is found inside the memory management unit hardware that helps speed up the paging process by mapping visual addresses to physical addresses without going through the page table. This device was developed to solve the problem of reduced system performance, which resulted from keeping many large page tables in memory for reference purposes, yet most programs tend to make a large number of references to a small number of pages and not the other way around, and thus only a small fraction of the page table entries are heavily read, while the rest are barely used at all. Therefore, in order to deal with the problem of keeping many pages, the page tables in memory, and thus improve the speed of paging, the computers were equipped with a small hardware device for mapping visual addresses to physical addresses without going through the page table. This device is called translation look aside buffer, or associative memory, and is usually found inside the memory management unit, just as we have already said. The associative memory consists of a number of entries, with each entry consisting of two parts, a key or tag and a value. When the associative memory is presented with an item, the item is compared with all keys simultaneously. If the item is found, the corresponding value field is returned. In addition, each entry contains information about one page. This information includes a bit that indicates whether the entry is valid, that is in use, or not, the visual page number, a bit that is set when the page is modified, the protection code, which is read, write, execute permissions, or with the read, write, execute permissions, and the physical page frame in which the page is located. These fields have a one-to-one correspondence with the fields in the page table. The TLB hit ratio is the percentage of times that a particular page number is found in the TLB, or the percentage of visual address translations that are resolved in the TLB rather than in the page table. This ratio can be increased by increasing the number of entries in the TLB. Related to the heat ratio is the TLB reach. This refers to the amount of memory accessible from the TLB and is achieved by multiplying the number of entries by the page size. The approaches of increasing the TLB reach are: number one, increasing the number of entries in the TLB. Number two, increasing the size of the page or providing multiple page sizes. The following figure is an example of some entries in a TLB. Under the valid, we have bit 1. Under the visual page, we have, for example, 140. When modified, it is indicated with 1. Protection is RW and the page frame that 1. And the same continues. And you can see that the visual pages are of different sizes. Under modified, we either have a 1 to indicate whether that page has been modified, and a 0 whether it is not. So any modified page can be indicated using bit 1 and unmodified one bit 0. Then under protection, we have different protection modes. We have different protection modes. Then under page frame, we have different page frames. The TLB is used with the page tables in the following way. The TLB contains only a few of the page table entries. When a visual or logical address is presented to the memory management unit for translation, the memory management unit first checks to see if its visual page number is present in the TLB by comparing it to all the entries simultaneously, that is, in parallel. If a valid match is found and the access does not violate the protection bits, the page frame is taken directly from the TLB without going to the page table. If the visual page number is present in the TLB, but the instruction it is trying to write on a read-only page, a protection fault is generated the same way as it would be from the page table itself. I repeat, if the visual page number is present in the TLB, but the instruction is trying to write on a read-only page, a protection fault is generated the same way as it would be from the page table itself. If a visual page number is not in the TLB, a TLB miss occurs and is detected by the MMU that does not, or that does an ordinary page table lookup. It then evicts one of the entries from the TLB and replaces it with a page table entry just looked up. If that page is used again soon, the second time it will result in a hit rather than a miss. When an entry is punched from the TLB, the modified bit is copied back into the page table entry in memory. The other values are already there. When the TLB is loaded from the page table, all the fields are taken from memory. Therefore, with associative memory, when a TLB miss occurs, instead of the memory management unit just going to the page tables to find and fetch the needed page reference, it just generates a TLB fault and tosses the problem into the lap of the operating system. The system must find the page, remove an entry from the TLB, enter the new one, and restart the instruction. If the TLB is reasonably large, for example, with 64 entries, to reduce the miss rate, software management of the TLB turns out to be acceptably efficient. The main gain here is a much simpler MMU, which frees up a considerable amount of area on the CPU chip for caches and other features that can improve performance. The normal way to process a TLB miss, whether in hardware or in software, is to go to the page table and perform the indexing operations to locate the page that has been referenced. The problem with doing this search in software is that the pages holding the page table may not be in the TLB, which will cause additional TLB faults during the processing. These faults can be reduced by maintaining a large, for example, 4 kilobyte software cache of TLB entries in a similar or in a fixed location whose page is always kept in the TLB. By first checking the software cache, the operating system can substantially reduce TLB misses. Some TLBs store address space identifiers that we abbreviate as ASINs in each TLB entry. An ASIN uniquely identifies each process and is used to provide address space protection for that process. When the TLB attempts to resolve visual page numbers, it ensures that the ASIN for the currently running process matches the ASIN associated with the visual page. If the ASINs do not match, the attempt is treated as a TLB miss. In addition to providing address space protection, an ASIN allows the TLB to contain entries for several different processes simultaneously. If the TLB does not support separate ASINs, then every time a new table is selected, for instance, with each context switch, the TLB must be flashed or erased to ensure that the next executing process does not use the wrong translation information. Otherwise, the TLB could include only entries that contain valid visual addresses but have incorrect or invalid physical addresses left over from the previous process. The use of associative memory helps avoid the overhead of translating visual addresses, but it's both expensive and power hungry. Congratulations, my dear students and the rest of the learners, for viewing and listening to this video on associative memory, which is part 7 of memory management topic. You can listen to the other parts of memory management topic, as well as other videos in the field of computers or ICT from MLSwap ICT YouTube channel. In addition, for you to be able to access free life skills, motivational and inspirational resources, visit MLSwap Motivation YouTube channel. I would also request that you subscribe to both channels in order to receive immediate updates whenever a new video is posted if you have not already done so. For any further correspondence, kindly write to us through the email emilyswap@gmail.com. Thank you very much and be blessed.